So thank you very much for the invitation. My name is Martin Monperrus. I'm professor of software technology at KTH in Sweden. And this workshop is a really interesting workshop because my first love in research is AI. Back in 2004, I published in NIPS, in neural computation. Before, in life, sometimes things happen and you change tracks. So I moved to software engineering, and a little bit later on, 2009, I started again to mix AI and software engineering. I was at the Technical University of Darmstadt in Germany, and we did a contribution where we put some piece of AI in the development environment, in something that is called the code completion system. It's the tool when you program which helps you to write the next thing. And so at that time, the state of the art was only to consider tokens or types, but no intelligence at all. And we did a first contribution in that direction, which later on was integrated into Eclipse and is now the key technology of a company in Darmstadt. And since then, so that was in 2009, and since then, in 2009 also, there was one of the very first paper about automated program repair. The first one in terms of visibility. So it's a paper by the University of Virginia, presented a system called GenProg. And so what the idea of this system is that it's a program which takes as input another program with a test suite. And in the test suite, there is one failing test. So the goal of program repair is to synthesize a patch such that this failing test passes, which would indicate that the bug has been fixed. But also, very importantly, the other test should still pass, which means that there is no regression. So this is the core idea back in 2009 of GenProg, and it's still the dominant way of stating program repair today, even if it's not the only one, and I will present two other ways of stating program repair. So this is the story back in 2009. So then I started to work on this and to put all my effort on this in 2010, 11 approximately. And so now we are like some years after, and so I can give you an answer. So can we train a program to repair other programs? The answer is yes. So this is the bottom line of this talk. The answer is yes. We can. But if today we go over all papers in the field of program repair and we sum all the bugs, the real bugs from real software that have been fixed correctly by the state-of-the-art of program repair, we would barely go beyond 100 bugs. Okay, so which means that the field is still at the beginning. So for some bugs, some open source projects which we could find in the history of packages, the program repair systems, including the ones made in my group, are capable to repair the bugs. This is where we are today. Now, so we have this huge AI momentum, and definitely there will be a way to leverage AI to go further. But for this, we need a lot of data. And this is the goal of this talk, is to present the kind of data we need to build the program repair systems of the future, 5 years, 10 years, maybe more. Because the thing is that, this was already said this morning by Lionel and then Robert again, that so deep learning has been made possible by CPU and data. So for instance, like image recognition. So the thing with image recognition is that it's quite easy to obtain training data because we can ask people in the world through Amazon Mechanical Turk, for instance, to label images. Okay, is there a car on this image? Is there a person on this image? They can even ask myself, when I use a website with a reCAPTCHA, I have to label images with either car or road signs. And the thing is that, so I'm labeling this data, and Google is using this data to train their systems. So basically what I'm saying here is that it's very easy to obtain a huge amount of data for training an image recognition system. But for program repair, what I need, so what the essence of the data I need to learn something, it's a bug and its fix, its human fix. And there comes a problem. I cannot ask on Mechanical Turk, Amazon Mechanical Turk, many persons across the world to fix real bugs in real software because it's a really daunting task. This is, by the way, what makes program repair interesting, because program repair is a human competitive task. Program repair today is done by humans, by educated developers, and so it requires the whole intelligence and comprehension of the software understanding. So we cannot collect this data. So what do we do? What are the alternatives to collect data for training a system to fix programs? So now we have to come back to the usages of program repair. So one usage is to put program repair in the development environment. So in this context, you imagine a developer at her workplace working on fixing a bug. So basically what she does is that she opens a bug repository, she picks a bug report, and then she reproduces the bug report, which means that she writes a test case with an assertion at the end of the test case, and running the test case, the assertion fails. This is the basic thing she needs. And then this developer would click on a button, repair. This is really the key usage of program repair in the IDE. So, writing a failing test case, clicking on the button repair, and going for a coffee. No, because it's time for coffee. Developer takes a coffee, go and chat with the roommates, come back to the machine, and say, and there's a pop-up, repair found. Excellent. Apply. So click on OK. And then in the IDE, there would be a change directly in the code with the patch. So far, so good. Does this give us data? Not yet. Where we would collect data is that the developer would see the patch and say, interesting. This is a correct patch. I committed to the code base. And so here we have a very important piece of data for learning, is that we have the developer assessment of the generated patch. She has said this patch is correct. This is very, very valuable because then we can feed a training system later on. So this is very good. And here we would also, another piece of very important data is that we would have the time between the first failure reproduction and the patch validated by the developer. Currently, the program repair systems are based on bugs from the past, taken from the commit history. And so basically what we see is that, okay, we take a bug from the past with a failing test case, with a patch, and we compare the patch generated by the machine and the patch generated by the developer. But what we do not know is whether the patch was human competitive, whether this was an easy patch at the time of, so back in 5 years ago. On the contrary, if we collect the repair data directly in the IDE, we can collect the patch, the human assessment, and the time for fixing it. So then we can really say whether program repair is human competitive or not. Now the second case is when the developer says, oh, okay, the patch passes the failing test case and all the tests, but it's actually incorrect. So then the developer would either say, okay, undo the patch, or slightly modify it to get a correct patch. And so in this case, we have again a very new, a very valuable piece of information to collect, is that the patch generated by the system is incorrect. And we also have the slightly improved version by the developer, which makes the patch incorrect into a correct patch. So here is a vision to collect this data. We have to write a plugin for the IDE, for Eclipse, for instance, that constantly collects failing test cases, run the program repair systems, and collects the assessment of developers according to the generated patches. If we start to do this right now on hundreds or thousands of machines, we would collect very valuable data for training a system to repair bugs. So this is the first way to collect data so that today, so that in the future we will be able to have the next breakthrough as in image recognition today in deep learning. Yeah.
Something on this, I guess. Why did you ignore the data that you already have in repositories as the first data?
We don't ignore it, so this is something we have. But it's incomplete because we don't have the time to repair. And also what we don't have is the human assessment of patch generated by the machine. So we only have the partial vision of the path, basically, what was captured in the community study. So, number one thing of this talk is so the vision of using program repair in the IDE and collecting in the IDE the data to run the system and the human assessment, the developer assessment of the generated patches. And for this, there is a lot of work to do. Yeah.
Why would the developer get a patch that passes all tests is incorrect? And because I want to link it to then, well, how do we learn anything from it if it is not related to any concrete piece of data that feed into the system? Meaning, if the system sees tests and the program, how do we learn from an answer that says the patch is incorrect or correct if we don't have any other concrete input?
Well, so, okay, the first answer, why is sometimes the patch incorrect? Because the test suite, in essence, is incomplete. It only covers some inputs and some paths. And so theoretically, of course, there are ways of making a set of test passing. There are many different ways of doing so. And in practice, it turns out that even with very strong test suites, according to the best industry standards and discipline, like in Apache projects, there are indeed a lot of patches possible to make a single test pass. So this is the answer. So why? Because the test suite is incomplete.
I want to link this to the second part. So that was also my assumption. But then how do we learn from an incorrect response from the developer?
Well, so we have here a data point, which is given this test suite and this training test case. So we had the program repair system had 100 patches, possible candidate patches, okay? he proposed one of them, which was incorrect. So we have a data point to train a system on top of this to rank the patches or to drive the search to the correct one.
Good. So my point is, this is not context independent. This is incorrect because there is another test case that is not documented, or there is a logic that is not documented, which may be different in a different system. So we cannot generically learn from it.
So there is no other test case available, otherwise it would have been detected. But there is a missing input, there is a missing assertion somewhere.
You cannot generalize this incorrect answer to learn the system, to teach the system.
Yes, because it's a data point to try to teach the system to identify the correct answer among the set of possible patches.
For this program, for this point of the program, but not for the next program, even if this is the
well,
same.
no, because the training will happen for a feature which is project independent. So the feature may be being, okay, does a Boolean condition contains a call to the contents method? Okay, this is a feature, and which would be used to select the correct patches. So there is some bits of context-independent knowledge that could be learned from this one data point given by the developer.
We can discuss this.
Let me be heretic here, or you're trying to address the problem. You're trying to address the problem of the test cases inadequately, or not completely specifying what the correct behavior should be. Maybe we have a situation such as Paolo mentioned where this is hard to describe. We also have now you try to learn from plenty of examples what the correct behavior could possibly be, and you want to look into the IDE in order to look what the response of the developer is, again in order to identify what the possible correct behavior should be. You know, as soon as you have a specification of what the correct behavior is, then the repair problem becomes much more concrete. Then you can always decide whether the repair is successful or not. You have a search space, you can aim for a particular search space. You can generate as many tests you like because you have an oracle. So many of the problems that you are trying to work around then go away. Why not simply assume that there is a specification?
Because this research is meant to be applicable in all companies where there is no such specification.
But how can you come up with a correct repair if there is no specification of what's correct?
We have an incomplete specification. We have the test suite. It's an incomplete specification. It's a partial specification, but it's still a specification. It's an executable one.
I don't know if I should let you continue or ask another question. You are saying the test suite is a specification, but this is like saying, a number of observations are the same as a mathematical function coming from.
No, it's not the same. It's a partial specification. It's a partial specification.
Yes. But given everything you just said, how could you claim so confidently that automating repairs is yes, definitely possible? Everything you just said.
No. I've only claimed that so far only 100% bugs have been repaired in the labs on past bugs, and I'm only explaining what kind of data we need to go to the next step. Maybe the next step is infeasible. Nobody knows. Or at least I don't know.
Or is that the case that certain type of bugs can be automatically repaired and others cannot?
Yes, so this is an interesting question. So the vision of automatic repair, as I said here, is not to repair all bugs. Okay? It's to repair a small fraction of them. So that's why it's really a trial. When the developer clicks on repair, she hopes that she has the time to go for a coffee and discuss with a colleague instead of working hard on the bug. Okay, and if it doesn't work, she still has to repair the bug. Here there is a third experiment to make, is that let's be very pessimistic and assume that we would only be able to repair 1% of bug reports, of bugs in the world. Okay? So how many bugs can there be in the world. Let's assume that a developer fixes, in average, 1 bug per day. Okay, it's a pessimistic assumption. So closes a ticket, 1 ticket per day. There are approximately, so there are more than 11 million developers in the world. So if you do the math, it's still hundreds of thousands of repaired bugs automatically repaired, so a lot of saved effort, basically. Okay, so now vision number 2. There are 3 visions here, and 3 different data we can collect. So the first vision is automatic repair in the IDE. The second vision is automated repair in the continuous integration pipeline. So what's continuous integration? The idea that for each commit, all tests are run on a version which is merged against other changes, other branches if you work in a Git setting. Okay, so basically, on each commit there is a build somewhere in a server. So in the open source world, it's on Travis, for instance. So there is a build somewhere, a CI build. And it is already documented, there are a number of empirical studies, that many CI builds fail. Which is good, because if they all succeed, it means that CI is useless. So the whole point of continuous integration is to fail, actually. So it's good to have CI failures. And so here we have another source of information. The goal of automatic repair is not to fix the test case in the IDE of the developer, but the goal of automated repair is to fix a build failure in the CI. So that's interesting. We have started to do so in a project called RepairNator, like Terminator, but for repair, so RepairNator. So what RepairNator does is that it monitors more than 400 open source projects on GitHub. It monitors the builds triggered for those open source projects, so the CI builds. And when there is a build failure, RepairNator tries to reproduce the build failure and to start a repair attempt. And then here we would get, and so RepairNator does this, and if there is an answer, RepairNator proposes a change to fix the build failure. So here we have another source of information, is similarly but differently to the developer in the IDE, we are able to compare the fix done by RepairNator and the fix done by the developer who handled the build failure, basically. What's interesting also is RepairNator is that, and it's related to your point on the kind of bugs, is that when we observe build failures, they are not exactly the same kind of failures that compared to test failures on the IDE. In build failures, we have integration failures due to the environment. We have check style, so code convention failures. And those failures call for different kinds of repair techniques. It's not the same thing to fix a failing assertion and to fix a check style assertion. It's a completely different, when you have a build failure due to the environment, the fix consists of changing the Docker image, changing the environment, the testing environment. And so in this case, the fix is different. So we would also collect, so by plugging like the mega version of RepairNator on top of a huge amount of projects, we would collect a lot of data on how to repair build failure, and so and how to train the system for this. Yes, Farid.
What is the current status of this research? You have data about what kind of issues you are able
So here, so in my group, we want to be the very first in the world to be able to fix a build failure before the human. We have started this in last January, January 1st, 2017, and so far, we have failed. So we did have patches, but they were incorrect patches in the sense of due to the incomplete specification. So we observed, we received the patches, and with my colleagues, we said, okay, even if we are not experts, this patch is incorrect. And we don't want the reputation of our robot to be ruined with an incorrect patch.
So no correct patch for
so far, no correct patch on test assertion failures.
And how many cases did you deal with? Just if you can share.
I have the exact numbers, which are here in my notes. So far we have considered more than 200,000 Java builds. 12,000 are failing builds. Among those 12,000, we were able to reproduce them locally, which is key. Okay, it's really hard if you consider real code to reproduce the bits locally. So we were able to reproduce 35%. So at the end, we have tried to fix 3,387 failing bits of Java projects.
And no correct patch?
No correct patch so far. And many kind of errors, because again, doing this in the large on real code, it's super challenging. There are so many things happening.
Because according to my experience, a lot of the bugs that you find in the software, several case studies, the fixes are simple sometimes. So it's strange that you were not able to fix anything.
These are not the bugs, these are just the integration.
Okay.
Yeah.
So is there hope with the third vision? Because so far, you have depressed us quite a bit with the first two. So.
No, come on! I don't want to depress you. I
half full you He didn't say half. He said he didn't manage to generate correct.
Well, that's even more opportunities. Come on, let's do it.
Yeah.
If it doesn't work, it just do it.
No, but it's interesting. I find this very motivating because it's basically it's ongoing work on something which is super hard and human competitive. Again, it's a human competitive task. So if we were able to do so in just a couple of months, come on, it would be too easy. No fun.
But is there some indication of progress?
Yes, there are a lot of yeah.
So what is it?
The indication of progress is that we are getting more and more patches. We also have here with this experiment, the Repanetor experiment, we have a very clear picture of the actual nature of build failures in the world. And interestingly, and maybe not surprisingly, the most common failures are not the ones handled by research. So this definitely calls for thinking. For research in specific areas. So for instance, coming back to the Czech style conventions here, there is a deep relation with this work on learning, machine learning coding convention, because then if you plug this in with an automated repair system, you have the complete loop of learning how to repair and repairing on the fly, so it's you close the loop basically. Vision number 3, or you are too depressed?
No, we need to go to vision number 3 now.
So vision number 3, it's related to, so this morning, we had this wonderful slide by Robert on the different kinds of AI. So here it's really about AI where we modify the code, the product, modify the source code. Now, let's go at runtime. We don't want to modify the source. We want to modify the execution. What it means. So this is the third vision. The third vision is that we have the same developer. Let's call her Madeleine. So Madeleine, she's a developer who clicked on repair in the IDE. Remember? A couple of minutes ago. She's Madeleine. She clicked on repair. So she had a coffee, she discussed, and then she went back to home. And so Madeleine is responsible for a system in production, an e-commerce system in production. And so when Madeleine, so she went back to home, and then she went to work again. And in the morning, so she arrived again, so she arrived at work, she took a coffee with her colleagues, and she opened her email box. And in her email box, Madeleine has an email from the production system directly saying, here is a patch. So how is it possible that the production system generates patches on the fly and sends them directly to the developer? So here, the idea is that there are techniques in the literature to modify the execution to overcome failures. So there are different names. So runtime repair is one name. Failure oblivious computing is another name. Self-healing software is a third name. But basically, all those techniques are about modifying the execution. There is one bit that we need to reason and to train a system on how to modify the execution. And this is what we have in production. If you have the e-commerce system handled by Madeleine. So in an e-commerce system, it's a web-based system. So at the end of, for each request, we have at the end an HTML and an HTTP output, which is an oracle, basically. It's a weak oracle, it's a partial oracle, but it's an oracle. So when you modify the execution at runtime, and this modification is correct according to the production oracle, so according, for instance, to the HTTP 200, you have a data point. When you modify the execution at runtime, and this gives you a failing request, you also have a data point. And so if you collect this data at runtime in production, you collect a whole lot of data on how to modify the execution so that you avoid crashes, unhandled exceptions, and so on and so forth. Yeah?
Sorry, I'm not sure that I got. So you have a system in production.
Yeah.
Okay? You receive an input from an end user.
Yeah.
Okay, and what you suggest is just to modify the execution or to modify the execution after the failure?
So just modify this. So coming to the failure, so this input triggers a failure. So for instance, a null pointer exception.
Okay.
And just modify this particular execution. So not the whole code, just this particular execution.
So you got an null pointer exception.
Yes.
And then you want to modify the execution.
Yes. And you resume the execution.
Okay, so you need a rollback mechanism somehow. Because you want to go back to the point before you received an input, or you need to record the data.
This is a technical implementation. There are different ways of doing so. Okay. Rollback is one way. Parallel shadow execution is another way. There are different ways of doing so. But the idea is that instead of simply crashing and end of the world, depressed, you try something. Okay? So you have multiple alternatives. And at the end you have an oracle. So then you can train the system to select the best modifications of the execution to come to the solution. Yeah?
What is the oracle?
Sorry?
What is the oracle exactly?
So for instance, the oracle can be whether, so if you modify the execution of a web input, an HTTP, the oracle can be whether the request ends with a HTTP 500, so internal server error, or HTTP 200, page server.
Realistically, this is not a realistic oracle.
Oh yes, it's very realistic. You have it for free in every web system.
Yes, but I can make a system that always gives an okay, but completely fails in terms of my business logic.
I completely agree. This is why it's a partial oracle.
And I can have, no, but
Yeah, so I
but I
completely
can have
agree.
a system that fails because something before failed, and by modifying the part that fails now, you're basically covering up the failure in the past. So you're actually propagating the error deeper into the system.
Well,
Because-
okay.
So let's say that I have a system that records something and fails to record part of the data properly. That I assume that had to be actually caught here. So it returns an okay. The data is corrupt, and this data comes up 2 hours later when I'm looking it up and fails, and there's a null pointer exception allowed.
Yeah.
How do you know that actually it was this morning in another request that the system failed?
So again, so this is a technical detail on how you handle the state. Let's take the simplest answer to this problem. So this is a very hard problem. The simplest answer is that you consider a stateless server system, like Amazon Lambda. You know this kind of thing we have now in the cloud. Serverless computing is super high, and so here it's stateless. So you can modify the execution as much as you want. You don't corrupt anything for the future. This is the first answer. There are many other answers depending on how you handle the state, but this is another issue.
So philosophically, one problem I have is that this is a much harder problem than your first vision. But on your first vision, you seem to be more careful with defining the problem, and here you seem to be more relaxed. Because in your first vision, you actually had a lot more data point to figure out what is happening. Here you actually don't have anything because you're looking into whether the system is healthy. And sometimes actually it's better if you build a system that crashes and comes up from the crash and recovers the situation and prepares a proper report than to covering up and fixing it. So here you're looking at a much more complex problem but simplifying it a lot, which to the point that it can become impractical, so it loses its visionary aspect.
No. So I here I strongly disagree. So first, because you don't mask anything, you can still log the crash as it would have happened without anything. Okay? So you still have the original data and monitoring insights. Okay, it's still there. You have something in addition to this.
Yes, but you're fixing the system, so the system will not create the same crash in the future. So I'm losing also crash data.
No, because at the crash point, you are still able to monitor and to log the behavior of the original application.
Yeah, now we are going a bit into detail, but if I have a system that crashes every 5 requests, at the end of the day, having 10 crash reports helps me to find the bug. If the system corrects itself after the first crash, so that I don't see the crash anymore, I never may be able to find the root of the bug, or I may not.
Well, no, unless the fix is the fix to the root of the bug, which is the vision. So it's exactly the point. Instead of having a developer analyzing the
you don't
10
have the
crashes.
logic of the program. The same thing that you assume you have when you said the programmer says something is incorrect. That if the programmer says something incorrect and you accept it, while your AI says this patch is correct, the tests passed everything, you still assume that there is an incorrect fix. But now here you assume that as long as your fix just provides an okay response, it's an okay fix.
No.
Ignoring the test and ignoring the program.
We have to reach a conclusion soon here.
Yeah, so
can
one
you
answer and one conclusion.
Conclude by taking.
But this is the sign of a very good talk, I have to say.
Yes.
Thank you. So one answer, one conclusion. So first, since you do this in production live, of course you can compare the same action, the same modification, the same patch, not for one crash, but for 1,000 crashes over different users. So you have much more external validity of the patch compared to the test case, because it counts for many inputs and many users. So this was a short answer. I hope it's enough. Now let's come back to conclusion. So I presented 3 visions of programming. The first one was in the IDE, with the button replay. The second one was in the CI, to build failures. The third one was in production, to modify the execution and generate patches out of production runs. And in all cases, to build the next generation of training I go with them. We need to collect this data. In all three visions, we need to collect much more data from development, from CI, and from production, so that we would have those huge data sets in 1 year from now, 5 years from now, and we could unleash the whole power of AI. Thank you very much for this.
Thank you.